Welcome back. In this section, we'll be looking at powers of a matrix. So we've seen diagonalization of a matrix, and we will show you this term, how it allows us to efficiently compute high powers of matrices. This will be useful in many applications of linear algebra, I like it, linear algebra, including Markov chains, which we'll cover next. So one thing that we'll use it for is to actually study long-term behavior of a Markov chain. All right, so let's start with an example. I mean, the method is pretty straightforward. It's a bit long, but it's pretty straightforward. So example 3.3.9, let's consider this matrix. It's the matrix of example 3.3.5. So we already have diagonalized it. So in example 3.3.5, we proved that D was P inverse AP. This is P, and this was our D. All right, so I want to compute high powers of A. I'm going to try to use D instead. So I want to compute D to the 10. All right, let me start with D squared. So that's minus 1, 0, 0, 0, 1, 0, 0, 0, 2 times minus 1, 0, 0, 0, 1, 0, 0, 0, 2. All right, so when I compute it, I get minus 1 times minus 1, and that's it. All right, next term I get 0, I get 0, get 0, and then I get 1 squared. I get 0, I get 0, I get 0, and then the final one I get 2 squared. Now that's interesting. See, I have the same pattern except that my diagonal entries are squared. Let's check that it works for D3, and then we'll make D3 is D2 times D. And so we've already seen that D2 is this. And so what happens when I multiply this with D again? Well, I'm going to get minus 1 times minus 1 squared, so minus 1 cube, 1 cube, 2 cube. And so in general, D10 should be minus 1 to the 10, 0, 0, 0, 1 to the 10, 0, 0, 0, 2 to the 10. And so I'm going to get 1, 1, 2 to the 10, 2, 4, 8, 16, 32, 64, 120, sorry, 2 to the 10,024. The computer scientist in me is a bit of shame right now, but yeah, 1024. All right, so let's try to use this to compute a to the 10. All right, so we want to compute a to the 10. We know that D is P inverse AP, and so that means A is P dP inverse, if I isolate A in that equation. And so if I looked at a to the 10, that's going to be P dP inverse 10 times. 1, 2, 3, 4. Let's keep going. All right, so P inverse P cancel, P inverse P cancel, P inverse P cancel. This one will cancel, this one will cancel. So really, you're left with a P at the start, then D, 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 and then P inverse. So it's P D to the 10 P inverse. And so since it's easy to compute the powers of a diagonal entry, that's what we'll do. So P we had found was 1, 1, 1, 0, 1, 0, 0, 5, 1. The D to the 10 we just got is 1, 0, 0, 0, 1, 0, 0, 0, 1024. And P inverse is 1, 4, minus 1, 0, 1, 0, 0, minus 5, 1. All right, and then all we have to do is multiply this out. Let's see, if I multiply, let's multiply these two first, I guess. It doesn't matter. So I get 1, 0, 0, and then the second one is 1, 1, 5, and then the last one is 1024, 0, 1024 times 1, 4, minus 1, 0, 1, 0, 0, minus 5, 1. And so when I multiply it, I get 1, I get 4 plus 1, 5, plus minus 5,000 and blah, blah, blah. So I get minus 5,015. And then this one I get minus 1, so I get 1,023. And this one is going to be 0. Then I'm going to get, wait, I'm going to get 1, and I'm going to get 0. And then this one I'm going to get 0. Right? Then I'm going to get 5. And then I'm going to get, wait, what did I do? So 4, 5 minus 5,120. And so again, that's 5,115 with a minus, and then 1,024. Good. All right, let's try to generalize this. If you want to compute dk, we said that was minus 1, 0, 0, 0, 1, 0, 0, 0, 2 to the k, and we have a shortcut. Just because it's diagonal, this won't be true in general. And so that middle one we could simplify a bit more. We said 1, 0, 0, 0, 2 to the k. And so if you want AK, by what we just did above, that should be P dk P inverse. And so let's just rewrite all of this. That's minus 1 to the k, 1 to the k, and then P inverse we said was 1, 4, minus 1, 0, 1, 0, 0, minus 5, 1. And so I get minus 1 to the k, 0, 0. And then I get 1, 1, 5, and I get 2 to the k, 0, 2 to the k. And then I want to multiply that by 1, 4, minus 1, 0, 1, 0, 0, minus 5, 1. And so that's going to give me minus 1 to the k, 0, 0. And then 4 times minus 1 to the k plus 1 minus 5, 2 to the k. I think I'm going to need more room. Sorry about that. I'm just going to move this here. All right, next one down, that will give you 1. And then further down, I'm going to get 5 minus 5, 2 to the k. And finally, over in the last column, I'll get minus 1 to the k. I could simplify that if I wanted to. 0, and then 2 to the k. And then here I would get 0. And finally, down in the corner, I'll get 2 to the k. All right, so I'll get minus 1 to the k, 0, 0, minus 1 to the k plus 1, minus 5, 2 to the k, and there you go. All right, It's a bit intense and a bit complicated. Well, there's a lot of little things, but it's not super hard. It's just a bit long. But what's nice is we've computed all the powers of A. And if you think of how hard that would be to try to find a formula for those powers, you could see that this is quite useful. And we'll really even start taking limits of these as k goes to infinity to try to see what the behavior is for big K.